This problem, we're told that number 6 fuel oil with a given viscosity and density flows in a 1.5-inch Schedule 40 pipe over a distance of 1,000 feet. The discharge point is 20 feet above the inlet, and the source and discharge are both at 1 atmosphere. We're told that a 15 horsepower pump that is 75% efficiency is used. We're asked to calculate what the flow rate is in the pipe. And so we have a bunch of given information here that we've assembled. Our properties, again, remember that for piping we need to look up what based on the nominal, what the actual inner diameter is. Our pipe length is 1,000 feet. And then what are we told? The inlet or the source is at atmospheric, as well as the outlet. The destination pressure is at atmospheric pressure. The power for the pump is 15 horsepower. The pump is 75% efficiency. We have a roughness factor for our commercial steel pipe, and then of course it's constant cross-sectional area, so it is we can calculate that right away. We don't know anything about the entrance and exit effects, so we're going to neglect that for now, so we don't worry about frictional losses there. Again, that may not be the best assumption, but that's what we're going to do for now. So no contractions or expansions. We're also not given anything about bends, elbows, fittings, or valves. So we're just going to consider the frictional losses due to the flow of the fluid in the pipe, in the friction with the pipe wall. This is a liquid. We are going to assume incompressible flow for all liquids that we're working with here. And so that means a continuity equation applies. We've got steady state. Another thing that we should realize as we're looking at this problem and we're getting used to solving these problems is that if we have constant cross-sectional area and incompressible flow, the mass flow rate, of course, is constant. The linear velocity is going to be constant from the inlet to the outlet, and the volumetric flow rate is going to be constant from the inlet to the outlet flow rate. So if we take all this information, we start to look at our Bernoulli equation, we can start figuring out what we need to, or what we can cancel out. So the pressure terms. Pressures are the same at the inlet and outlet. Also, the density is the same at the inlet and outlet, so those pressure terms go away. We already mentioned the linear velocities are the same at the inlet and outlet, so those go away. What about the discharge level? Well, at the discharge at position 2, that's going to be 20 feet higher. We'll use Z1 as our datum, so that'll be 0. And what are we left with? Well, we're left with head loss, which is what we're going to have to account for. No head extracted, that is for turbines and expanders only. And then our head added, we're told, is 15 horsepower from the pump. And so our Bernoulli equation simplifies down to something that is a pretty simple equation. Head added minus head loss is equal to Z2. What were we asked to find? We were asked to find the flow rate. How are we going to do that? Do we see flow rate in here? We see no velocity in here. So we can't use, remember, the mass flow rate is equal to rho times linear velocity times cross-sectional area. That's not anywhere in here explicitly. What are we going to do? Well, if you think about it, remember that head loss is going to be proportional to, is going to be, or I should say, going to be a function of velocity, right? So we have a velocity that's buried in here. Also remember that the head added, we are told that it's 15 horsepower. The pump is 15 horsepower, 75% efficiency. Remember, power is equal to head times the weight of the fluid, which is rho g, times the volumetric flow rate. So our flow rate, or our velocity, however you want to think of it in terms of mass flow rate, linear velocity, or volumetric flow rate, it is actually buried in these two terms. So anyway, what we will have to do is we will have to eventually expand these terms to include the functional dependence on linear velocity and then solve for the linear velocity. So let's start doing that. So the first thing I want to do is start to calculate the head losses, and this is only due to friction. And we worked another problem. What we found is that generally process flows involving things that have the viscosity of water are usually going to be turbulent. We've run into some cases where process type flows with oils tend to be laminar, and the reason is because number one, the density is a little lower, but the viscosity, moreover, the viscosity is much higher than water, and so that means the Reynolds number is going to be a lot lower than what we would have if we were dealing with something that was like water. So what we will do is we will make an assumption that our flow is going to be laminar. So if our flow is laminar, our fanning friction factor is 16 over the Reynolds number, or 16 times viscosity over rho ID mu, U. So here's our velocity in the pipe. We can then calculate the head loss, right? We can go through and we can calculate the head loss, and after we make all those assumptions, this is the formula that we get for the head loss. And so here is, buried in here is the velocity that we are after. Notice 32 constant, mu, that's constant, length of the pipe, that's constant, rho, that's constant, g, that's constant, id is constant. So here is the velocity buried in this head loss term. Now for the pump is 15 horsepower, right, and 75% efficient. But what that means is that less than 15 horsepower is delivered to the fluid, right? And so if we do this calculation, let me bring this over here. The power that is actually delivered to the fluid is going to be the power that is given to that is the pump is rated at times our efficiency. So only 11.25 horsepower is added to the fluid, right? And then if you remember the relationship between the head added to the fluid and the power, right, is the head added the relationship between the head added and the power that is added to the fluid is the weight of the fluid times the volumetric flow rate. So what we can do now is we can put this term in to this term of our Bernoulli equation. So now our head added has the linear velocity. So we take this, substitute it into our Bernoulli equation, we take our head loss, we substitute it into our Bernoulli equation, and then we make that, do that calculation. Here's what we get. Again, we can afford to be a little lazy algebraically when it comes to using MathCAD, so I'm going to use the root function. So I'm going to guess a linear velocity of 1 meter per second. I'm going to take this function, plug it into my MathCAD root function, ask it to calculate for u, or linear velocity, and we get a linear velocity of 1.164 meters per second. From there, we can calculate the mass flow rate and the volumetric flow rate. We get a mass flow rate of 1.5 kilograms per second. And I realize I'm mixing and matching between SI and American Engineering. But in our volumetric flow rate of 0.054 cubic feet per second. And again, I should have done this earlier, but we need to calculate and make sure that our Reynolds number is indeed laminar for this assumption that we made. And yes, we have a Reynolds number of 59, much less than 2300. And so yes, we do have laminar flow. Now notice that we do not have any frictional losses due to fittings. And as we mentioned in other problems, if you do have fittings, those can be significant. So be very careful about when you do these problems what your assumptions are, and realize that if you do put fittings, bends, elbows, valves, contractions, expansions into these lines, you really need to go back and redo those calculations because those head losses can be significant.